Graphs are one of the most important and widely used data structures, and it has many applications in real life. Many things in your day-to-day life can be modeled as a graph problem. In this video, I will try to give you an introduction to graph, what are the different applications of graphs, and we will also look at the different types of graphs that are commonly used. So let's begin. First of all, what is a graph? So here you can see a diagram of a graph. So let's see its definition. What is it? These nodes and edges, what are these? So a graph can be written as a set of two things, V and E, where V is the set of vertices. So if you look at this graph that is given here, here the vertices are A, B, C, D and E. Similarly, these arrows denote the edges. So this V will contain A, B, C, D, E. If we look at the previous graph, and edges, this E is set of edges. So vertices can be represented like this, and in some real scenario, these may not be just one level, but this can be a data structure in itself. For example, let's say we are trying to model the followers and followee on Twitter. So maybe A is following B, but B is not following A, and there are some other persons as well. So each person will have a name, will have a ID, will have a date of birth, creation date, email ID and many other things. So this whole thing, one person will denote one node or one vertex. So, but for simplicity and for understanding the concepts, we generally denote these nodes with some labels, either 0, 1, 2, 3, 4 or A, B, C, D like this. So that's the vertices. Now this relationship is an edge. It can be directed or it can be undirected, which we will shortly see. So graph represents pairwise relationship between a set of objects, and it is made of two components. We have already seen that. First component is vertices. We also call these nodes or points. Second component is edges. We call them links or arcs as well. Now let's see some of the types of graph. So graphs can be directed, it can be undirected. For example, we saw the example of this Twitter case where A is following B, but B is not following A. So this is not equivalent to B. Arrow going from B to A is different from arrow going from A to B. But there can be scenarios where this is not important. Let's say we have two houses are there and there is a path between them. So there is not any notion of direction here. So a person from here can go to here and he can return using the same path. There is no notion of direction, that is, this house you can go here but cannot come back. So you can think of other scenarios also where the direction is not important, but sometimes the direction is important. So these are the two different types based on the direction of edges or order of vertices. So in directed, if we have a ordered pair UV are vertices. So this is first vertex and this is second vertex, and you can think of an edge going from U to V and we represent it as UV. If we write VU, then this will mean that there is an edge going from V to U and not U to V. So this ordering is important. So that's the case with directed. But in undirected case, UV is same as VU and we represent it as this. So you don't see any direction here. These are connected. These both are friends. A is a friend of V, or let's write U and V. U is a friend of V and V is also a friend of U. So it's mutual relationship. So there is no direction here. So let's look at other categorizations of graph based on some other criteria. So this was based on the ordering of vertices along the edges. Then the second category is based on weights. So some graphs may be undirected, unweighted. So we don't write the weights on the edges. So if we don't write weights, you can also think them as 1. So that is unweighted case, but there can be weights also. For example, if we have cities, this is city A, this is, let's say, San Jose. This is, let's say, San Francisco. And let's say we have some place Santa Clara here. So there is a notion of weight here. This is much closer to this. So it can be, let's say, 30 miles. And this can be, let's say, 50 miles. So this is important here. And similarly, there can be, you can think of some chemical bonds in some chemical structures. Let's say we have double bonds, then we have single bonds. So we can think of them as strong bonds and much stronger bonds, and these are very weaker bonds. So there is a notion of weights. We can model different kind of relationship with the help of edges. These edges denote the relationship between these nodes, and there are different ways of modeling it. It can be distance, it can be one person following somebody else, it can be friendship, how close they are friends. If, let's say, these are very close to each other, it means that they are very close friends, and there are some other people also in the network. That means they are acquaintances, but they are not too close friends. So this edge can model different kinds of relationship. Now let's look at some of the applications of graph. So we have already seen one example of social network, Twitter. Similarly, it can be Facebook, it can be Instagram, it can be LinkedIn, and it has a good application in social network. So this person, these are connected, these are friends, let's say, and let's say these are in some common group. There are some groups on these all social networking sites. Let's say these are in a group called computer vision group. They are interested in these. Maybe they are researchers working on computer vision applications, and this person is much more interested than others, and that person is part of some other groups also, maybe some other group of image processing, as well as some other group on mathematics, NLP, and so on. So you can model different kind of scenarios using these graphs, especially for social networks. Then we can think of dependency graphs. So let's say a simple example can be dependency of courses. So you must have done some courses in the college, or you are still doing. So there you straight away cannot take a course which is in 4th year. First you have to complete the courses of 1st year. So maybe you need to do CS 101 before you can do CS 201, or maybe later you do CS 550. I am writing some imaginary course name. So in order to do CS 550, you need to do CS 201. Maybe this is a prereq for another course as well. Let's say EE 680. So until you do this, complete this course, you cannot complete these courses. Similarly, until you complete CS 101, you cannot complete this. And here generally you will not find a cyclic dependency, that CS 101 is dependent on 550. So generally this kind of dependency will not exist in course prerequisites. So this can be modeled as a graph. Here again there is a notion of direction here. Then you can model cities, which cities are connected and how well they are connected. You can have different cities. You can have let's say Bengaluru, you have Hyderabad, you have New Delhi, and maybe there are lots of flights going between these cities. Every day there are maybe 10 flights, but maybe between New Delhi and Hyderabad there are only 4 flights. So you can model this connectivity using this, and maybe there are indirect flights also. Maybe it goes to Kolkata and then comes to New Delhi. So all of this can be modeled as a graph. Now let's see some of the more types of graphs. We had seen directed, undirected, and we had also seen weighted, unweighted. But apart from those categorization, there are many more types of graphs. So let's have a look at them. So we will in particular look at these graphs. There are many more, but we will not go into the details of each and every graph. We will mainly look at these 7 graphs again. So first is regular graph. So what is regular graph? Here each vertex has same number of neighbors. That is, each node has same degree. So let's try to draw one. Let's say we have 5 nodes and degree is 3 for each node. So let's draw some 3 edges. So this has a degree of 3. Now this has 1, so draw 2 more. Now this has a degree of 3. This has a degree of 1. Now this has also degree of 3. This has a degree of 3. We cannot draw any further. So what we will do, let's get rid of this. I did not pick a good example here. So now this graph, in this graph, every vertex has connectivity of 3. So in general, if the degree is k, we call it k regular graph, and in this case it is 3 regular graph. And you don't need to have a connectivity between all of them. Maybe you have one more graph where every node is connected to 3 nodes. You can think of some example. So in this case in particular, we have drawn a complete graph. We will see what is a complete graph, but that was not the intent. The intent is that every node has same degree. This can be cycle as well. Let's say this is a cycle. So this is not a complete graph. All the edges are not present, but still it's regular graph since it has a degree of 2, 2, 2, 2, and it's 2 regular graph. So I hope a regular graph is clear here. Now let's look at complete graph. So here each pair of vertices is joined by an edge. So let's draw nodes first of a graph. Let's say we have 5 nodes. So each node is connected to every other node. So did we miss any edge? Yes, this one. Now this is complete graph. All the nodes are connected to every other node. Let's take example. Let's say node are 1, 2, 3, 4 and 5. Let's write which nodes are connected to 1. 2 is connected using this edge. 3 is also connected. 4 is also connected. 5 is also connected. So 1 is connected to all the other nodes. Similarly, you can write the connectivity of other nodes and you will see that it's connected to all other nodes. So this kind of graph is a complete graph. This is also a complete graph with 4 nodes. This triangle is also a complete graph. So that's the definition of complete graph. But if you write, this is not a complete graph. Since these two vertices are not directly connected, they are connected, but they are not directly connected by a direct edge. So this is not a complete graph, but all these 3 are. Now let's look at the next example. It's called connected graph, and here we will differentiate between undirected and directed graphs. In the above examples, in the above types, we had not made any distinction between that. So here for undirected case, we will have 2 types, connected and disconnected. That is, let's say we have this graph. So this is connected. Since there is no notion of direction, so we can go from any node to any other node following a path. So if we want to go from here to here, we will first come to here and then come here. Similarly, you can pick any pair of nodes and they are connected by some path. And in the case of disconnected, let's say you remove one of the edges, let's say this one, now it becomes disconnected. You cannot go from any of these three vertices to any of these two vertices. So this will be disconnected. So here it's very clear. In directed, we have some more notations due to the direction case. So let's look at strongly connected. So first we need to understand what are strongly connected vertices. So strongly connected vertices means if you pick a pair of vertices UV are strongly connected if there is a path, directed path from U to V. That is, from U you go to some other vertex, and finally you reach V. So direction is important here. So if this kind of path exists from U to V, then you see that UV are strongly connected. But if that's not the case, we will say that they are weakly connected if you remove the directions. So if you remove the direction, in directed case they are not connected for all the nodes. For example, let's say from this I can go to here, from this I can go to here, from here also I can go to here, but from here I cannot go to this node. If there is an edge we can go here, but still from here we cannot go here. So this is not strongly connected. So this is not strongly connected, but we will see is it weakly connected. So for that, get rid of the direction. So redraw the graph, but without direction this time. Now this is connected. So we will call it weakly connected. So this will be weakly connected, but if you add some more edges like this one, now I think you can go from any node to any other node. For example, here you can, let's say if you want to go from this node A to B, then you will go to this node C, and then from here you will take this edge to reach B. Similarly, you can go from any node to any node. So this will be strongly connected, but if this edge is not there, this will be weakly connected. But there may be scenarios that even by removing the direction, they are not connected. For example, this case, so this component is strongly connected. You can go from any node to any node, but this is just one graph. But from any of these, you cannot go to any of these using any path. Even if you remove the direction, you will get this graph, this kind of graph. Still they will be disconnected even after removing the direction. Then we will call them disconnected. Now let's look at some more graphs. Bipartite graph. So here a vertex set can be partitioned into two sets, W and X, such that no two vertices in W share a common edge. So let's say we have edges like this. First draw the vertices, and then we have a few more vertices. So if this kind of graph is there, then you can partition the vertices into two sets. Let's call this yellow vertices as W and the blue vertices as X. Now you will notice that there is no edge between the vertices of same set. This is one set, this is another set. You see that there is no edge like this. So if there is an edge like this, then this will become a non-bipartite. Since in this set we have an edge going like this, and if you move this blue to this side, again you will have this edge that is going from this to this. So if you move it this side, again that will be between vertices of the same set. If it's here, there is a edge from this blue to this blue, so this will be non-bipartite. But if we remove this, now it's bipartite, since we can partition the vertices into two sets such that no vertices in W share a common edge and no vertices in X share a common edge, and it can be two colored, this bipartite graph. So coloring means that no two adjacent nodes should receive the same color. So if this is color C1, this should receive a different color. So let me draw it like this, bar over the C1, that means any other color. So this can be in general K coloring, that is no two adjacent vertices will have same color. If we have three colors, then if this is color 1, then this can be 2 or 3 but not 1. So in this case this can be two colored, which is equivalent to not having a edge between the sets of between the vertices of same sets. And this is sometimes also called chromatic number, the number of colors you require to color a graph such that no two adjacent vertices receive the same color. So that's called chromatic number, and for bipartite graphs the chromatic number will be 2. Then we have planar graphs. That means vertices and edges can be drawn in a plane such that no two edges intersect. For example, if you draw a triangle, it has 3 vertices and 3 edges. We have drawn it and none of the edges intersect. So don't count these vertices as intersection points. These edges start from this vertex and ends at another vertex. So we will not call these vertices as an intersection point. It should be like this. So they are intersecting but there is no vertex here. So this kind of thing should not exist. So this is a planar graph, since all vertices and edges are drawn without edges intersecting. Similarly, if we have 4 vertices, then this is planar. If we add this, then this is planar, still planar, none of the edges are intersecting. And if we connect these two also, still they are not intersecting. So even with 4 vertices, we can draw a complete graph. Each node is connected by a direct edge to all the other nodes. So this is also planar. But let's say if we have five nodes, so let me redraw it. This is 4th node, this is 5th node. So now you can make these connections, it's planar. You make this connection, it's planar, still planar. Now which are the edges left? So this is a planar graph, but if you add this edge, it's still planar. Now which vertex is left? This one is left. So you can draw this also, still it's planar. So till this point it is planar. Now what is the connection left? Let's say this is A and this is B. There is no edge between A and B. And if we draw it like this, then it intersects here with this edge, so it becomes non-planar. So let's try other things. If we draw it like this, then it intersects here, so again it will become non-planar. So there is no way you can draw an edge between A and B now without making it unplanar. So if we draw this, then this will become unplanar or non-planar. So that's the definition of planar graph. Next is a very important kind of graph called cyclic or acyclic, and that is defined by the presence or absence of cycle. So the cycle means that you can go from A to B, B to C, C to D, and again you come here. So if this is A, B, C, D, so this forms a cycle. This node is not part of the cycle, but there is a cycle here. So this will be called cyclic graph. Similarly, in undirected case, its equivalent will be this. So this is also cyclic. This is also cyclic. But if you look at this example, then this is not cyclic. There is no cycle here. So this is acyclic. We don't call it non-cyclic but acyclic, and these are cyclic. Next type of graph is tree. So trees are also graphs, and these are undirected graphs. So you should not get confused with the binary trees, which you must have read, where we have a notion of left and right child. So you implicitly think of a direction, but in general trees fall under the category of undirected graph. So let's draw a tree. 1, 2, 3, 4, 5. So this is a tree. It's undirected and there is no cycle. So between any two pair of nodes, let's pick 2 and 5. So what is the path between 2 and 5? You come from 2 to 1, from 1 to 5. Similarly, if you want to go from 2 to 4 or 6 to 4, what you will do? You will come to 1, then you will come to 3, then 4. Is there any other path? No. So that's the condition for tree. Any two vertices are connected by exactly one path. So in essence, a tree is a connected. So if you add a few nodes here, and let's say that these all are part of the same graph, then this will not be a tree. These are not connected. Because if you pick one node here and one node here, the number of paths between these two is 0. But we have defined that the path should be exactly 1. So not less, not more. So this will not be a graph, not be a tree. But this part, if you look at just this part as a graph, then this is a tree. So this is connected. If this is not connected, it will not be a tree. We know the definition of connected. Then it should be acyclic. We know the definition of acyclic. It should not have cycles. If it has cycle, then it will have multiple paths. Then undirected, we know the definition of undirected, and we know the definition of graph. So a tree is a connected, acyclic, undirected graph. Now we are done with the different major types of graph. You can explore further types of graphs. There are many more types of graph. Now there is a very important concept in graphs. That concept is called adjacency. So let's see what is meant by adjacency. So there is adjacency defined for vertices as well as edges, but generally in most scenarios we are talking about adjacency of vertices. So two vertices are called adjacent if they share a common edge. So let's draw a graph, and let's draw it like that. So we have A, B, C, D and E. So is A and D adjacent? So the definition said that if they share a common edge. Is there a common edge between A and D? No. A and D is connected with the help of B. So we need to take two edges in order to reach from A to D. So first go to B, then D. So A and D are not adjacent. The answer is no. Is B and E adjacent? Again the answer is no, since there is no direct common edge between B and E. But if we ask, is B and C adjacent, we see that there is a common edge between them. So it will be yes. If we draw an edge like that, then B and E will become adjacent. So that is the notion of adjacent vertices. Similarly, there is a notion of adjacent edges also. If edges share a common vertex, for example, this edge, let's call it E1, and let's call this edge E2. These are adjacent because they share a common vertex B. So, but that notion is not that much used as adjacent vertices. So for now we will be focused on adjacent vertices. Now let's solve this problem based on your understanding of graph. So it will give you some idea how well you are understanding the graph data structure. So in the first slide we had seen that graph is made of set of vertices and edges. So I have given you the set of vertices and set of edges. Try it yourself, then I will give the solution here. Now let's try to build this graph using this information. So first, the set of vertices are 1, 2, 3, 4, 5, 6. That means there are 6 nodes. So let's draw it. 1, 2, 3, 4, 5 and 6. So we have drawn the nodes. So this part is done. Now we don't need this. Now let's look at the edges or the connectivity. So 1 and 2 is connected. So connect them. 1 and 4 is connected. Next 2 and 3 are connected. 2 and 4 are also connected. 3 and 5 is connected. 5 and 6 is connected. So this is the graph that is being represented using this set of vertices and edges. So I hope it was a good introduction to graphs and its different types and its application. In future lessons we will see it how we can represent graph programmatically. So we will see different representations of graph, and the two major representations would be adjacency matrix and adjacency list. There are other representations like this edge list. Even if this is not given to you, you are just given this, then you can build this graph. If you are given that there is only one component in this graph, let's say there is a node 7 also, but it's not connected to anything else, so the edge list will not capture this information. So you cannot build this graph from this. So you need the vertex information as well. But if the graph is connected, you can build the graph from just this set of edges.